Have you ever stopped to think about what's actually happening inside your smartphone the exact second you tap the screen? Or, how these massive AI accelerators process billions of calculations in what feels like the blink of an eye? We always hear about gigahertz and terabytes, but right beneath all that overwhelming complexity lies a surprisingly simple mechanism, a microscopic switch. Actually, billions, sometimes literally trillions of them, working in perfect silent unison. So today, we're going to unpack this explainer on the CMOS inverter, which is absolutely the foundational building block of our entire modern digital world. Okay, let's dive right into this. Because frankly, understanding this one tiny component is the absolute key to unlocking how every single digital device on the planet functions. We're going on a bit of a journey here, starting from the macro devices we hold in our hands every day, all the way down to the microscopic logic that breathes life into them. We're going to see exactly how a remarkably simple concept of opposites forms the bedrock of all modern computing. So here's our roadmap for this explainer. We'll start with the heart of all chips. Meet our key players, PMOS and NMOS, and watch their dance of opposites. Then we'll take a deep dive into voltage transfer and noise, explore their power, speed, and efficiency, and finally, look at how they build our digital world. Section 1. The hearts of all chips, defining the inverter. At its core, an inverter, which you'll often hear called a NOT gate, does exactly what its name suggests. It is the ultimate contrarian of the digital world. If you feed it a logical high, or a 1, the output becomes a logical low, or a 0. And if you give it a low, it just flips it right back to a high. On a circuit diagram, it's pretty easy to spot. It's a triangle pointing forward, capped with a tiny little bubble. And that bubble, that's the universal symbol for inversion in electronics. It's a beautifully simple concept, but it is absolutely essential for a computer to process any kind of logic. Moving on to Section 2, meet PMOS and NMOS, the complementary pair. Now, the C in CMOS is really the secret sauce here. It stands for complementary metal oxide semiconductor. And complementary just means we're using two different types of transistors that act as perfectly opposing switches. First, you have the PMOS transistor at the top, which is connected to the power supply, known as VDD. It turns on when the input is low, and it turns off when the input is high. Right beneath it is the NMOS transistor, and that one is connected to ground. It does the exact opposite. It turns on when the input is high and turns off when it's low. Section 3. The dance of opposites, how it works. Because PMOS and NMOS have these totally opposite characteristics, feeding them the exact same input makes them react, well, inversely. If the input is a 0, the PMOS wakes up and turns on, while the NMOS stays completely off. The result, you get a 1 at the output. Flip that input to a 1, and the PMOS shuts off, the NMOS turns on, and the output drops down to a 0. Crucially, and this is a big deal, they never fight each other. Only one conducts at a time. This prevents a short circuit and guarantees a crystal clear output every single time. Let's trace the actual path of the current here. Imagine our input is low, meaning 0 volts. This low signal triggers our top switch, the PMOS, instantly turning it on. At that exact same microsecond, our bottom switch, the NMOS, stays completely off. So our output wire is now physically connected straight through that active PMOS switch up to the VDD power supply, while the path down to ground is totally blocked off. Because of that, the output gets pulled all the way up, giving us a final output of a high 1. Now, think about what happens when we flip the input too high, driving it up to the VDD voltage. Instantly, the PMOS transistor receives that signal and shuts off, severing its connection to the power. Simultaneously, the NMOS transistor at the bottom wakes right up and turns on. Now the output is connected directly to ground through that NMOS switch, which immediately drains the voltage away. So your final output becomes a firm, safe, low 0. Let's head into Section 4, Voltage Transfer and Noise, the deep dive. We're looking at the voltage transfer characteristic, or VTC. Imagine you're slowly turning a dial to increase the input voltage from 0 to maximum, rather than just flipping a light switch. In region 1, the input is low, and the output stays perfectly high. But as we keep turning that dial, we hit region 2, which is the transition region. Here, for a very brief, frantic moment, both the PMOS and NMOS transistors are actually partially conducting. The output falls rapidly as it swings from high to low. Finally, we reach region 3, where the input is definitively high, the PMOS is completely shut off, the NMOS takes over entirely, and the output flattens out at completely low. Within that voltage curve, engineers basically obsess over a few specific parameters. VOH and VOL are simply your maximum and minimum output voltages, but VIH and VIL, those are your critical gatekeepers. VIH is the absolute minimum voltage the input needs before the gate officially declares, okay, I'm calling this a high. VIL is the maximum it will accept as a low. And sitting dead center is VM, the switching threshold. So if your power supply is 1.2 volts, your VM is balanced perfectly right around 0.6 volts. It's the ultimate tipping point. So why does all that highly specific voltage threshold stuff actually matter? Well, it all comes down to noise margin. Look, in a complex circuit packed with billions of transistors, there is unwanted electrical noise everywhere. Think of it like trying to have a conversation in a super crowded, loud restaurant. The noise margin is essentially the amount of electrical static or interference a signal can pick up before the inverter gets confused and accidentally misreads a 0 as a 1 or vice versa. Larger noise margins mean way greater reliability against all that interference. And, thanks to its clean transition curve, CMOS has absolutely fantastic noise margins.
Section 5. Power, Speed, and Efficiency. The CMOS Magic.
The single most crucial number to remember for CMOS is 0. That is the exact amount of static power this inverter consumes when it's just sitting there, doing nothing but holding a 1 or a 0. Why is that? Because either the PMOS is on or the NMOS is on, but never, ever both. It's exactly like a plumbing system where one valve in a pipe is always firmly shut. Water simply can't flow through. This near-zero static power consumption is the true magic of CMOS. Think about it. If they constantly leaked power, the billions of transistors inside your smartphone would literally melt the device right in the palm of your hand. But wait, if it uses zero static power, why do your devices still get hot and drain the battery? The answer is dynamic power. Energy is consumed when the inverter actually switches states, frantically charging and discharging these microscopic wires. The variables driving this are super interesting. Alpha represents how often it switches. CL is the load capacitance, basically the size of the electrical bucket it has to fill. F is your operating frequency or gigahertz, so faster switching naturally means more power. But pay close attention to VDD, the supply voltage. Notice that it's squared in the formula. This is exactly why engineers fight tooth and nail to run modern chips at the lowest possible voltages. It's all to save your battery life. And that brings us to speed, or what we call propagation delay. The inverter is incredibly fast, yes, but we still can't break the laws of physics. It takes a tiny, finite amount of time for a signal to push in, trigger the transistors, and actually change the output. We measure this in two ways, high to low time and low to high time. The average of these tiny fractions of a nanosecond dictates the absolute maximum speed, or clock frequency, at which your processor can actually run. Section 6. Building the digital world. Scale and synthesis. When you sum up all the core engineering benefits of the CMOS inverter we've talked about, it becomes really clear why it completely wiped out all older logic designs. It gives us near-zero static power, incredibly high switching speed, and excellent noise immunity. But for sure, the absolute game changer here is its extreme scalability. It is remarkably easy to shrink this design down to advanced microscopic technologies without losing a single one of those benefits. And that scalability is exactly why this precise arrangement of two complementary transistors basically runs our modern world. By combining multiple CMOS inverters, engineers build complex logic gates like AND and NAND. Those gates then build the microprocessors in your laptop and form incredibly dense SRAM memory caches. They are literally the foundation of the massive AI and machine learning accelerators driving today's technological revolution. And they scale flawlessly down to the 7, 5, and even 3 nanometer nodes being manufactured right now. All of this leaves us with a pretty fascinating question to ponder as we wrap up this explainer. We've seen how the CMOS inverter fundamentally relies on distinct on and off states, carefully managed voltages, and keeping electrical noise at bay. But as we shrink these transistors down to just a few dozen atoms wide, hitting that 3 nanometer mark and looking even beyond, how much smaller can this foundational pair of transistors actually get before quantum physics and pure electrical leakage just completely get in the way of the logic? It is quite literally the multi-billion-dollar question driving the future of electronics. But hey, at least now you know exactly how the foundational piece of that puzzle actually works.